Look at any photograph of the night sky taken from a dark place, and you will see something that feels intimate. Stars scattered like salt across black velvet. Perhaps the faint blur of a distant galaxy. The impression is one of stillness, of permanence, of a cosmos frozen in place while we drift through our brief lives beneath it. That impression is one of the most dangerous lies in all of astronomy. Right now, at this very moment, the Milky Way is moving. Not drifting, not wandering. Moving with intent, with direction, with a speed that would vaporize your comprehension if you could feel it against your skin. Our entire galaxy, all 400 billion stars, all the planets orbiting them, all the moons orbiting the planets, every asteroid and comet and grain of interstellar dust. The supermassive black hole at the centre, and you, lying wherever you are listening to this, is hurtling through space at approximately 1.3 million miles per hour. Say that number slowly, 1.3 million miles per hour. At that speed, you could travel from Earth to the Moon in just over 11 minutes. You could reach the Sun in about 4.5 days. You could cross the entire diameter of the solar system, from the orbit of Neptune all the way back around to the other side, in roughly 2 months. And we have been travelling at this speed for billions of years. But here is the part that keeps cosmologists awake at night, the part that has haunted astronomy since 1973, and still has no clean answer. We are not travelling at random. We are not coasting. We are being pulled. Something out there, hidden behind the plane of our own galaxy, shrouded by hundreds of millions of stars that block our view like a curtain drawn across a window, is dragging the Milky Way toward it. Not just the Milky Way. The Andromeda Galaxy is coming too, so is the Triangulum Galaxy. So are all 50-odd members of our local group. So are the galaxies in the Virgo cluster, 11 million of them, and the galaxies in the Centaurus supercluster, and the galaxies in the Hydra supercluster. Hundreds of thousands of galaxies spread across a region of space 300 million light-years across are all falling in the same direction, toward the same hidden point, like leaves caught in a current none of them can see. That point has a name. Astronomers call it the Great Attractor. And after 5 decades of searching, 5 decades of radio telescopes and infrared surveys and X-ray observatories, 5 decades of the most sophisticated gravitational mapping ever attempted by human beings, we still do not fully understand what it is. Tonight, we are going to follow the current. We are going to trace the path that our galaxy is carving through the universe, follow the pull that has been shaping cosmic structure since the first seconds after the Big Bang, and arrive, or as close as we can arrive, at the centre of the largest gravitational mystery in the observable universe. If you find these slow journeys through the strange architecture of existence worth your time, consider tapping that like button and subscribing. These videos are built for the quiet hours, for drifting and thinking and falling asleep to, and your support helps them continue. Now settle in. Let us begin. To understand what the Great Attractor is, and why it remains so stubbornly difficult to see, we need to first understand something about our address in the universe. Not just our location, though that matters, but our situation, the peculiar and somewhat frustrating circumstances of where we happen to be standing. Picture yourself inside a house. The house has many windows, and through most of them you can see clearly. The yard, the street, the neighbouring homes, the hills in the distance. But one of those windows faces directly into a thick hedge. The branches and leaves are so dense, so tangled, so close to the glass, that when you look through that particular window all you see is green. You know there must be something on the other side. A field, a road, perhaps another house. But you cannot see it. The hedge is in the way. The Milky Way galaxy is our house, and we live inside it, about 2/3 of the way out from the centre, embedded in one of its spiral arms. From our position, we can look out in most directions and see the universe clearly. We can observe galaxies billions of light-years away. We can photograph the cosmic microwave background, the faint afterglow of the Big Bang itself, stretching across the entire sky. The universe is relatively transparent to our instruments, except in one direction. When we look toward the centre of our own galaxy, toward the bulge of ancient stars and dense gas and dust that marks the Milky Way's heart, our view becomes obstructed. Not just obstructed, obliterated. The plane of the galaxy, that bright band you can see stretching across the summer sky from a dark location, is filled with so much intervening material that visible light from objects beyond it cannot reach us. Astronomers call this region the zone of avoidance. It stretches across roughly 20% of the sky, and for most of human history it was simply a mystery. A blank spot on the map. Here there be dragons, because here we cannot see, and the Great Attractor sits almost exactly in the centre of that zone. Let that settle for a moment. The most massive gravitational concentration within hundreds of millions of light years of Earth, the thing that is pulling our galaxy and 100,000 others toward it, is located in the one direction where our view is most thoroughly blocked. It is as if the universe is playing a cosmic joke, placing the most important piece of the puzzle in the one spot where we cannot quite make it out. This is not coincidence. The same flattened disk structure that gives the Milky Way its distinctive spiral shape, the same concentration of stars and gas that creates the zone of avoidance, is also the reason we're moving toward the Great Attractor in the first place. Gravity does not care about lines of sight. Gravity does not care that we cannot see where we're going. It pulls anyway, silent and patient and utterly indifferent to the frustrations of any species trying to understand it. And so for decades, astronomers have been trying to peer through the curtain. First with radio telescopes, which can detect wavelengths of light that pass through the dust more easily than visible light. Then with infrared telescopes, which can see the faint heat signatures of distant galaxies even when their starlight is blocked. Then with X-ray observatories, which can map the hot gas that fills the space between galaxies in massive clusters. Piece by piece, observation by observation, they have been assembling a portrait of what lies behind the hedge. What they have found is both more and less than they expected. The story of the Great Attractor begins, like so many stories in modern cosmology, with a measurement that did not quite fit. In the 1970s, astronomers were busy mapping the expansion of the universe. They had known since Edwin Hubble's work in the 1920s that distant galaxies are receding from us, that the universe is expanding, that the fabric of space itself is stretching and carrying galaxies along with it, like raisins in rising bread dough. But they wanted to measure this expansion more precisely. They wanted to know exactly how fast the universe is growing and whether that growth is uniform in all directions. To do this, they needed to measure the velocities of galaxies. They did this using redshift, the phenomenon where light from a receding object is stretched to longer, redder wavelengths, just as the pitch of an ambulance siren drops as it drives away from you. The more a galaxy's light is redshifted, the faster it is moving away from us. Measure enough galaxies, and you can map the flow of the universe itself. But velocity measurements are tricky, because galaxies have two kinds of motion. The first is the motion caused by the expansion of space, the Hubble flow, named after Edwin Hubble, which is smooth and predictable and depends only on how far away a galaxy is. The second is peculiar velocity, the motion caused by local gravitational influences, by nearby masses pulling galaxies this way and that, adding to or subtracting from the Hubble flow. To separate these two kinds of motion, you need to know not just how fast a galaxy is moving, but how far away it is. And measuring cosmic distances is hard. It requires finding objects of known brightness, standard candles, astronomers call them, and comparing their apparent brightness to their intrinsic brightness. The dimmer they appear relative to how bright they actually are, the farther away they must be. In 1976, a team of astronomers led by Vera Rubin, the same Vera Rubin who would later provide crucial evidence for dark matter, published a paper that included a curious observation. When they measured the velocities of galaxies in different directions and compared them to the expected Hubble flow, they found an asymmetry. Galaxies on one side of the sky seem to be moving slightly faster away from us than the expansion of space alone would predict. Galaxies on the opposite side seem to be moving slightly slower. This suggested that the Milky Way itself was moving through space, not just being carried along by the expansion, but actually travelling with a peculiar velocity of its own. And the direction of that motion pointed toward a region of sky in the southern constellation Centaurus. At the time, the observation was controversial. Other astronomers could not reproduce it. Some suggested it was a systematic error in the distance measurements. The Rubin team's peculiar velocity seemed too large, too coordinated, too strange to be real. But then, in 1987, a group of 7 astronomers published a paper that would change everything. They were known as the 7 Samurai, a playful name, but the work was deadly serious. Using a new technique for measuring galaxy distances, one based on the relationship between a galaxy's rotation speed and its total luminosity, they mapped the peculiar velocities of hundreds of elliptical galaxies across a vast region of the nearby universe, and they found the Great Attractor. Let me try to give you a feel for what they discovered. Picture the universe within a few 100 million light-years of Earth. In your imagination, you are floating in intergalactic space, and all around you are galaxies, hundreds of thousands of them. Some are small and faint, mere dwarf galaxies with a few billion stars. Some are giants, great ellipticals containing trillions of stars, their golden light speaking to ancient stellar populations that finished forming when the universe was young. These galaxies are not scattered at random, they are clustered. They gather in groups and clusters held together by gravity. Our local group is one such cluster, a few dozen major galaxies dominated by the Milky Way and Andromeda. Nearby is the Virgo cluster, containing over 1,000 galaxies, anchored by the giant elliptical M87 at its centre. Farther out is the Centaurus cluster, the Hydra cluster, the Norma cluster, each one a concentration of mass in the otherwise thin soup of intergalactic space. But when the Seven Samurai mapped the peculiar velocities of galaxies across this region, they found something unexpected. All of them, not just our local group, not just the Virgo cluster, but all the galaxies within roughly 200 million light-years, were participating in a coordinated flow. They were all moving in the same general direction, towards something. The Seven Samurai called this coordinated motion a bulk flow, and they traced it to a point in space located roughly 150 to 250 million light-years away, in the direction of the Centaurus constellation, hidden behind the zone of avoidance. They called this point the Great Attractor. Stop and feel the weight of that for a moment. Something out there is massive enough to influence the motion of hundreds of thousands of galaxies across a region of space 300 million light-years wide. Massive enough to create a coordinated flow that spans a significant fraction of the observable universe's local structure. Massive enough to be pulling our own galaxy, right now, at this very moment, at 1.3 million miles per hour, toward a destination we cannot quite see. The Seven Samurai estimated the mass required to produce this effect. The number they arrived at was staggering, approximately 10,000 times the mass of the Milky Way. In more absolute terms, something like 100 million billion solar masses, that is, the mass of 100 million billion stars like our Sun, concentrated in a single region of space. But when they looked in that direction, when they aimed their telescopes toward the Great Attractor's coordinates, they could not see enough galaxies to account for that mass. This was the mystery. This was the problem that would occupy cosmologists for the next 4 decades. Something was pulling us. Something enormous. Something hidden. And even when astronomers began to peer through the zone of avoidance with radio and infrared instruments, even when they finally started to see the galaxies lurking behind the dust, they could not quite find enough mass to explain the pull. Where was it? To answer that question, we need to zoom out even further. We need to leave our comfortable neighbourhood of nearby galaxies and see the universe on a scale that makes even the Great Attractor look local. Because the Great Attractor, it turns out, is not the end of the story. It is not the centre of the pull. It is merely one step in a gravitational cascade that spans 500 million light-years. But before we take that step, let us linger here for a moment. Let us feel the strangeness of our situation. You're lying down somewhere, perhaps in a bed, perhaps on a couch, perhaps on the floor with your eyes closed. You feel stationary. The surface beneath you feels solid and still. Perhaps you can hear distant sounds. Traffic, wind, the hum of an appliance. Everything feels local, human-scaled, present. But you're not stationary. You're rotating with the Earth at roughly 1,000 miles per hour at the equator, somewhat slower at higher latitudes, and you cannot feel it because the rotation is constant, and you have been doing it your entire life. The Earth is orbiting the Sun at 67,000 miles per hour, and you cannot feel that either, because the motion is smooth and there is no wind in space to push against you. The Sun is orbiting the centre of the Milky Way at 450,000 miles per hour, carrying the Earth and all the planets with it, and you cannot feel that because the orbit takes 230 million years to complete, and you will not live long enough to notice the curve. And beneath all of that, underneath all those nested motions, the entire Milky Way is falling toward the Great Attractor at 1.3 million miles per hour. This is your true motion through the universe. This is your actual velocity. And it has been your velocity since the moment you were born, and it was your parents' velocity before you. And it was the velocity of the dinosaurs and the trilobites and the first bacterial cells that flickered into existence in Earth's ancient oceans. For 4.5 billion years, this planet has been falling toward a point in space it will never reach. Why will it never reach? Because the universe is expanding faster than we are falling. This is the cosmic joke at the heart of the Great Attractor. We are being pulled toward it. Yes, our peculiar velocity carries us in its direction every second of every day. But the expansion of space is carrying the Great Attractor away from us even faster than we are approaching it. We are like a swimmer trying to reach a boat that is being carried away by a stronger current. We swim, and the boat gets farther away. In another 100 billion years, the Great Attractor will have receded beyond the cosmic horizon, beyond the edge of the observable universe, and even its gravitational influence will be too weak to detect. Our descendants, if any exist, will look out into a sky that seems even darker, even emptier, even more alone than the sky we see tonight. The memory of the Great Attractor will live only in ancient databases, in the records of a species that once looked up and wondered what was pulling them. But that is the distant future. Let us return to the present, to the mystery that remains unsolved. Where is the missing mass? When astronomers finally managed to peer through the zone of avoidance in the 1990s and 2000s, using radio telescopes and infrared surveys and clever computational techniques to subtract the foreground stars, they found what they expected to find. Galaxies. Lots of them, clustered together in exactly the way gravitational attraction would predict. They found the Norma Cluster, one of the largest and most massive galaxy clusters in the nearby universe, located almost exactly at the coordinates of the Great Attractor. They found it hiding behind the thickest part of the zone of avoidance, which is why it had gone undetected for so long. The Norma Cluster contains thousands of galaxies, anchored by the massive elliptical galaxy ESO 137 G006, and its total mass is substantial. 10 trillion solar masses, perhaps more. But 10 trillion solar masses is not 100 million billion solar masses. The Norma Cluster, large as it is, accounts for only a fraction of the Great Attractor's inferred mass. Where is the rest? This question led astronomers to a realization that reshaped our understanding of cosmic structure. The Great Attractor is not a single object. It is not even a single cluster. It is a region, a vast diffuse concentration of matter that includes the Norma Cluster, and dozens of other clusters and superclusters, all embedded in the same general overdensity of the cosmic web. Let me try to give you a picture of what this means. The universe is not uniform. It was nearly uniform in the beginning, in the first few 100,000 years after the Big Bang, when matter was spread almost evenly across all of space. But there were tiny variations, quantum fluctuations magnified by cosmic inflation, and these tiny variations meant that some regions had slightly more matter than others. Over billions of years, gravity amplified these variations. The dense regions grew denser as matter flowed toward them. The sparse regions grew sparser as matter drained away. And the result is the cosmic web, a vast three-dimensional network of filaments and walls and nodes, with great voids in between where almost nothing exists. The clusters and superclusters we see are the nodes of this web. The filaments are rivers of galaxies and dark matter connecting the nodes. The walls are vast sheets of matter, paper-thin on cosmic scales but spanning hundreds of millions of light years. And the Great Attractor is not a node. It is something bigger. It is an entire region of the cosmic web that happens to be denser than the regions around it. Think of it this way. Imagine you're looking at a topographic map of a continent. You see mountains and valleys, ridges and basins. The Great Attractor is not a single mountain peak. It is an entire elevated region, a plateau perhaps, or a broad highland, where the average elevation is higher than the surrounding plains. The Norma Cluster is one of the peaks on that plateau, but the plateau itself is what creates the pull. This picture explained why the Seven Samurai could not find enough visible matter to account for the Great Attractor's mass. The mass is real, but it's distributed across a vast region of space, much of it in the form of dark matter, the invisible substance that makes up roughly 85% of all the matter in the universe. Dark matter cannot be seen directly. It does not emit light. It does not absorb light. It interacts with ordinary matter only through gravity. But its gravitational pull is real, and when you add up all the dark matter in the Great Attractor region, all the dark matter halos surrounding all the galaxies and clusters, all the dark matter filaments connecting them, all the dark matter spread across the intervening space, you get a mass concentration sufficient to produce the observed bulk flow. The Great Attractor is not a hidden object. It is a hidden structure. But this is where the story takes another turn, because the Great Attractor, vast as it is not alone, and it is not the deepest part of the current we are caught in. In the years following the Seven Samurai's original discovery, astronomers continued to map the peculiar velocities of galaxies across ever larger regions of space, and they found that the bulk flow toward the Great Attractor did not stop at the Great Attractor. It continued beyond it. The galaxies in the Great Attractor region were themselves moving, pulled by something even farther away, even more massive, even more hidden. In 2014, a team of astronomers led by R. Brent Tully, one of the original Seven Samurai, published a paper that redrew the map of our cosmic neighbourhood. Using the most detailed velocity data ever assembled, they identified a structure they called Laniakea. Laniakea is Hawaiian for immense heaven, and the name is appropriate. Laniakea is not a cluster. It is not even a supercluster in the traditional sense. It is a basin of attraction, a region of space within which all galaxies are flowing toward a common centre. That basin contains the Milky Way, the Local Group, the Virgo supercluster, the Great Attractor, and hundreds of thousands of other galaxies. Its diameter is roughly 500 million light-years. Its mass is 100 million billion solar masses, the same figure the Seven Samurai originally estimated for the Great Attractor alone. What the Seven Samurai had actually discovered, it turned out, was not the Great Attractor itself. They had discovered Laniakea's gravitational centre, and the gravitational centre of Laniakea is not exactly where the Great Attractor was thought to be. It is near the Norma cluster, yes, but the true centre of the basin, the deepest point in the gravitational well toward which everything in Laniakea is falling, is a diffuse region that includes the Great Attractor but extends beyond it. The Great Attractor is not a destination. It is a waypoint, a gravitational rest stop on a journey that has no end we will ever reach. Let that settle for a moment. And even Laniakea is not the end of the story. Beyond the edge of Laniakea, astronomers have detected evidence of even larger structures. To the south and east, Laniakea is bounded by a vast cosmic void, the dipole repeller, as it was named in 2017, a region of space so empty that its relative lack of gravity pushes galaxies away from it. The dipole repeller is not pulling us anywhere. It is simply so empty that the surrounding matter flows away from it, like water draining around a rock. And in the opposite direction, beyond the Great Attractor, beyond the far edge of Laniakea, astronomers have identified an even more massive concentration of matter. They call it the Shapley supercluster. The Shapley supercluster is the most massive concentration of galaxies within 1 billion light-years of Earth. It contains at least 8,000 galaxies clustered into at least 20 distinct clusters, all gravitationally bound, all participating in the same cosmic structure. Its total mass is estimated at 10 quadrillion solar masses, 100 times the mass of Laniakea, 100 times the mass the Seven Samurai originally attributed to the Great Attractor, and the Shapley supercluster is pulling us too. When cosmologists model the bulk flow of galaxies in our neighbourhood, they find that approximately half of our peculiar velocity, half of that 1.3 million miles per hour, comes from the Great Attractor and the Laniakea basin. The other half comes from the Shapley supercluster, 600 million light-years away, exerting its gravitational influence across an expanse of space that light itself needs 600 million years to cross. We are being pulled in two directions by two immense gravitational concentrations, one hidden behind our own galaxy, one barely visible on the edge of our cosmic horizon, and both of them are receding from us even as we fall toward them, carried away by the expansion of the universe, never to be reached. There is something almost melancholy about this picture, something lonely. Here we are, on a small planet orbiting a small star in a modest galaxy in a vast supercluster, being dragged through the universe by forces we cannot see toward destinations we cannot reach. The current that carries us is older than the Earth, older than the Sun, older than the stars we see at night. It has been carrying matter toward these gravitational basins since the first structures began to form in the infant universe, hundreds of millions of years after the Big Bang, and it will continue carrying matter until the expansion of space tears the cosmic web apart, until the filaments thin and the clusters disperse and the universe grows so cold and empty that gravity loses its last faint grip on reality. We are passengers on a journey that began before life existed and will end after life is forgotten, and the universe does not care whether we understand it or not. But we do understand it, at least a little. That is the strange miracle at the heart of this story. We are small and brief and fragile, and yet we have figured out that we are moving, figured out where we are going, figured out the shape of the basin we are falling into. We have named the Great Attractor and mapped Laniakea and measured the pull of the Shapley supercluster. We cannot feel our motion, but we can calculate it. We cannot see our destination, but we can infer it. That seems like it should count for something. Now, before we go further, before we explore how astronomers actually peer through the zone of avoidance, before we trace the history of the bulk flow measurements, before we ask what all of this means for the fate of the universe and our place within it, let me return to where we started. You're lying down somewhere, in the dark, perhaps already drifting towards sleep. Above you, if you could strip away the ceiling and the atmosphere and the light pollution of human civilization, you would see the stars, and among those stars, hidden by their collective glare, hidden by the dust and gas of the Milky Way's spiral arms, is the Great Attractor. You cannot see it. You will never see it with your eyes. But it is there, and it is pulling you right now, at this very moment, at more than 1,000,000 miles per hour. You feel nothing. The pillow beneath your head feels solid. The room feels still. But you are falling. Everyone you have ever loved is falling with you. Every city and forest and ocean on Earth is falling. Every planet in the solar system is falling. Every star you see at night is falling, and so is every star you cannot see, and so is the black hole at the centre of our galaxy, and so are all the galaxies in the local group, and so are all the galaxies in the Virgo cluster, and so are all the galaxies in the Laniakea basin, and so is the Great Attractor itself, falling toward the Shapley supercluster, which is falling toward something else, which is falling toward something beyond that, in a cascade of gravitational pulls that extends across the observable universe and perhaps beyond. There is no stillness in the cosmos. There is only falling, and the fall has no bottom. In the chapters ahead, we will walk through the science that revealed this picture. We will meet the astronomers who first detected our galaxy's motion through space, who first suspected that something was pulling us, who first named the thing they could not quite see. We will explore the zone of avoidance and learn how modern instruments have begun to penetrate its dusty veil. We will examine the structure of the cosmic web and ask why gravity gathers matter into clusters and superclusters rather than spreading it evenly across space. We will confront the role of dark matter, the invisible substance that makes up most of the Great Attractor's mass and most of the mass in the universe. And we will ask the question that every cosmologist eventually faces: does any of this matter? Not in the scientific sense. Of course it matters scientifically. The bulk flow of galaxies tells us about the distribution of matter in the universe, about the initial conditions of the Big Bang, about the nature of gravity on cosmic scales. These are profound questions with profound answers, but in the human sense. Does it matter that we are falling? Does it change anything to know that our galaxy is being pulled through space by a gravitational anomaly we cannot reach? Does it help, or hurt, or do nothing at all to understand that the universe is structured this way? Vast and hierarchical and indifferent, currents within currents, falls within falls, all the way down? I do not know the answer. Nobody does. But the question feels worth asking. It feels worth sitting with, in the dark, while the Great Attractor pulls you through another few hundred miles of empty space. And so let us continue. The year is 1976. In a basement laboratory at Lawrence Berkeley National Laboratory in California, a physicist named George Smoot is staring at data that should not exist. He has been working on an experiment designed to measure something called the cosmic microwave background radiation, the faint afterglow of the Big Bang, the oldest light in the universe, released when the cosmos was only 380,000 years old. This light has been travelling through space for 13.8 billion years. It should be the same temperature everywhere you look. That is what the simplest models of the Big Bang predict. The universe expanded uniformly, cooled uniformly, and the ancient light should be uniform too, a perfect bath of microwave radiation at 2.7 25 degrees above absolute zero, identical in every direction. But Smoot's data shows something else. The cosmic microwave background is not uniform. It is warmer in one direction and cooler in the opposite direction. The difference is tiny, about 3 millikelvins, or 0.003 of a degree, but it is there, and it is consistent, and it appears night after night in the measurements. Smoot and his colleagues spend months checking their instruments, looking for errors, looking for contamination from Earth's atmosphere, or radiation from the Milky Way, or some flaw in the experimental design. They find nothing. The signal is real, and what it means is startling. The cosmic microwave background radiation is not actually warmer on one side of the sky. The radiation itself is uniform, just as the Big Bang models predict. What Smoot is seeing is a Doppler shift. When you move toward a source of light, the light appears slightly bluer, slightly more energetic, slightly warmer. When you move away from a source, the light appears slightly redder, slightly less energetic, slightly cooler. This is the same effect that makes an ambulance siren sound higher pitched when it approaches you and lower pitched when it drives away. It works for sound waves. It works for light waves. It works for microwave radiation. And if the cosmic microwave background appears warmer in one direction and cooler in the opposite direction, there is only one explanation. We are moving. The Earth, the Sun, the entire Milky Way galaxy is moving through space relative to the cosmic microwave background, relative to the oldest light in the universe, relative to the rest frame of the cosmos itself. Stop and feel the weight of that for a moment. Before 1976, astronomers knew that the Earth orbits the Sun, that the Sun orbits the centre of the galaxy, that the galaxy rotates, but they assumed that the Milky Way itself, as a whole, was essentially stationary in space. Oh, it might drift a little here or there, nudged by nearby galaxies, but the universe was thought to be homogeneous on large scales. The average motion of galaxies in any large volume should cancel out to zero. The Milky Way should be roughly at rest with respect to the cosmic average. Smoot's data said otherwise. The Milky Way is moving at about 600 kilometers per second, more than 1.3 million miles per hour, in a specific direction in the sky, toward a point in the southern constellation Centaurus. This is not rotational motion or orbital motion. This is bulk motion, translational motion, the entire galaxy sailing through space like a ship crossing an ocean. The discovery raised an immediate question. Why? What is pushing us, or pulling us, or carrying us along at such tremendous speed? The Milky Way is not a small object. It contains somewhere between 100 billion and 400 billion stars, plus vast quantities of gas and dust and dark matter. Its total mass is roughly 1 trillion times the mass of our Sun. To move something that massive at 600 kilometers per second requires an enormous amount of gravitational influence. Where is that influence coming from? The obvious first guess was the Virgo cluster. Virgo is the nearest large galaxy cluster to the Milky Way, containing somewhere between 300 and 2,000 galaxies, centered about 54 million light-years away in the direction of the constellation Virgo. It is a natural candidate. The Milky Way is gravitationally bound to the Virgo cluster. We are part of its larger gravitational neighbourhood, slowly falling toward it. Perhaps our high velocity is simply the result of Virgo's pull. But there was a problem. The direction did not match. The Milky Way is moving toward a point in Centaurus, not toward Virgo. Virgo is nearby in celestial terms. They are both in the same general region of the sky. But the direction of our motion is offset from Virgo by several tens of degrees. This meant that something else was contributing to our velocity. Something in addition to Virgo, something perhaps much farther away and much more massive. Throughout the late 1970s and into the 1980s, astronomers worked to refine the measurements. They needed to separate the different components of our motion. The Earth's orbit around the Sun, the Sun's orbit around the galactic centre, the Milky Way's motion relative to nearby galaxies, and the motion of our entire local region relative to the cosmic rest frame. Each of these motions has its own direction and speed, and they all add together like vectors to produce the total motion we observe. The work was painstaking. Every measurement had multiple sources of uncertainty. The cosmic microwave background dipole, That temperature difference between one side of the sky and the other gave the total velocity, but passing it into components required independent information. Astronomers needed to know the distances and velocities of thousands of nearby galaxies. They needed to model the gravitational pull of the Virgo cluster. They needed to account for the motion of galaxies in our local neighbourhood, the local group. And when they did all of this, when they subtracted out every known component of motion, something was left over. Even after accounting for Virgo, even after accounting for everything visible within a few 100 million light years, there was a residual velocity. We were still moving, still being pulled towards something farther away, something that could not be seen in ordinary optical surveys, something hidden. In 1987, a team of 7 astronomers, Alan Dressler, Sandra Faber, David Burstein, Roger Davies, Donald Lyndon Bell, Roberto Turlevich, and Gary Wegner, published a paper that would change our understanding of the local universe. They had spent years measuring the distances and velocities of hundreds of elliptical galaxies using a technique called the Faber-Jackson relation, which links the brightness of an elliptical galaxy to the speed at which its stars are moving. By comparing observed velocities to the velocities predicted by uniform expansion, they could map the gravitational flows in our cosmic neighbourhood. What they found was remarkable. Galaxies were not moving randomly. They were streaming, flowing, converging. Across a vast region of space, hundreds of millions of light years wide, galaxies were falling toward a common destination. Not just the Milky Way, not just the local group, not just the Virgo cluster. Thousands of galaxies containing trillions of stars were all being pulled in the same direction. They called this destination the Great Attractor. The name was deliberately provocative. Dressler and his colleagues knew they could not see what was doing the attracting. The flow convergence pointed toward a region of the sky, in the direction of the constellations Centaurus and Norma, precisely where the Milky Way's disk blocks our view. The zone of avoidance. Whatever was pulling all these galaxies was hidden behind the densest part of the galactic plane, obscured by dust and stars, invisible to the optical telescopes of the day. They estimated its location at roughly 150 to 250 million light-years away. They estimated its mass at something like 10 quadrillion solar masses, 10,000 trillion times the mass of our Sun, perhaps the equivalent of tens of thousands of Milky Way-sized galaxies. But these were estimates, inferences from the motions of other objects. The Great Attractor itself remained unseen. Let me try once more to give you a feel for what this picture represents. Imagine you're standing on a beach, watching the water. You see waves approaching the shore, and you understand that the waves are caused by something out in the ocean. The wind, perhaps, or a distant storm. But now imagine that instead of waves, you see all the water in the ocean slowly draining away from you, flowing towards some point on the horizon. Not just the surface waves, the entire ocean, all of it, moving relentlessly in one direction. You cannot see what is draining it. The horizon cuts off your view, but you know from the motion of the water that something is there, something with immense pulling power, something that is affecting everything you can see. That is what the 7 astronomers discovered in 1987. The local universe is draining. Galaxies are water, and they are all flowing toward a hidden point on the cosmic horizon. The response from the astronomical community was immediate and contentious. Some researchers were skeptical. The measurements required for bulk flow studies are extraordinarily difficult. You need accurate distances to thousands of galaxies, and distance measurement in astronomy is notoriously uncertain. Different distance indicators can give different results. Selection effects, biases in which galaxies you happen to observe, can create spurious signals. Several groups attempted to replicate the work using different techniques and different galaxy samples. Some confirmed the flow, others found different velocities, different directions, or no significant flow at all. Throughout the late 1980s and 1990s, the Great Attractor became one of the most debated topics in observational cosmology. Was it real? Was it an artifact of measurement error? If it was real, what was it? A supercluster of galaxies? A wall of galaxies? Some exotic concentration of dark matter? And why was it so massive? Standard models of structure formation, based on the gravitational growth of small initial fluctuations in the early universe, could produce galaxy clusters and superclusters, but something as massive as the Great Attractor seemed to require unusually large initial seeds. The The answers began to emerge slowly, as new observational techniques allowed astronomers to peer through the zone of avoidance. Optical light is absorbed and scattered by interstellar dust, but other wavelengths pass through more easily. Infrared light, with its longer wavelength, can penetrate dust clouds that block visible light. Radio waves pass through almost unimpeded. By shifting to these wavelengths, astronomers could begin to see what lay behind the galactic curtain. In 1986, the year before the Great Attractor paper was published, the Infrared Astronomical Satellite, or IRAS, completed an all-sky survey in infrared light. This survey revealed thousands of previously unknown galaxies hiding in the zone of avoidance. Some of them were enormous. Some of them were exactly where the Great Attractor was supposed to be. One cluster in particular stood out. It was called Abell 3627, located about 200 million light-years away in the direction of the constellation Norma. In optical images, it was barely visible, a handful of faint smudges obscured by foreground stars. But in infrared, it blazed. This was one of the most massive galaxy clusters in the nearby universe, containing hundreds of large galaxies packed into a relatively small volume of space. Its discovery was like finding a city that had been hidden by fog. But Abell 3627 was not alone. Further surveys using radio telescopes and infrared instruments revealed that the Great Attractor region was not a single massive object, but a complex of structures. There were multiple clusters, multiple filaments, multiple walls of galaxies. The region was dense with matter in a way that is unusual by cosmic standards. It was not a point source pulling the local universe toward itself. It was more like a broad, diffuse concentration, a gravitational well into which galaxies were sliding from all sides. And then came an even more surprising discovery. The Great Attractor was not the end of the story. It was not the final destination. It was just a waypoint. In the early 2000s, astronomers began to measure bulk flows on even larger scales. Instead of studying galaxies within a few 100 million light-years, they pushed out to 1 billion light-years and beyond. And what they found was that the flow did not stop at the Great Attractor. The Great Attractor itself, along with all the galaxies falling toward it, was moving. The entire complex was being pulled towards something even more distant. That something was the Shapley supercluster. The Shapley supercluster, also known as the Shapley concentration, is one of the largest structures in the observable universe. It lies about 650 million light-years from Earth in the direction of the constellation Centaurus, and it contains a staggering collection of more than 8,000 galaxies packed into 24 or more individual clusters. Its total mass is estimated at more than 10 quadrillion solar masses, comparable to the Great Attractor, but located 3 to 4 times farther away. Despite this greater distance, Shapley's pull is felt across an enormous volume of space. Think about what this implies. The Milky Way is falling toward the Great Attractor at 600 kilometers per second, but the Great Attractor is also falling toward Shapley, and Shapley presumably is falling toward something else. Perhaps an even larger concentration of matter beyond the edge of our surveys, or perhaps just the cumulative pull of vast filaments and walls of galaxies stretching across the cosmic web. Gravity does not have a limit. It does not stop at some particular distance. Every mass in the universe pulls on every other mass in the universe. The pull falls off with distance. According to Newton's law, it weakens with the square of the distance, but it never disappears entirely. The Great Attractor pulls on us. Shapley pulls on us too, but more weakly because it is farther away. And every other concentration of matter in the universe, the Coma Cluster, the Perseus-Pisces supercluster, the Sloan Great Wall, exerts its own tiny tug. The motion we observe at 600 kilometers per second toward Centaurus is the sum of all these pulls. It is the result of the entire distribution of matter in the universe, integrated across all directions and all distances. In a perfectly uniform universe, these pulls would cancel out. The matter on one side of us would balance the matter on the other side, and we would sit still. But the universe is not perfectly uniform. It is lumpy. It has clusters and voids, walls and filaments, superclusters and supervoids. And wherever there is more matter in one direction than another, there is a net gravitational pull. There is motion. In 2014, a team of astronomers led by R. Brent Tully at the University of Hawaii published a paper that attempted to map this structure on an even grander scale. They called their work the Laniakea supercluster, from the Hawaiian words for immense heaven. What Tully and his colleagues showed was that the Milky Way, the local group, the Virgo cluster, the Great Attractor, and tens of thousands of other galaxies all belong to a single gravitational basin. Like streams flowing down a mountainside into a valley, all these galaxies are flowing toward a common centre of gravity. The Laniakea supercluster contains roughly 100,000 galaxies, and spans more than 500 million light-years across. But even Laniakea is not the end. The Shapley supercluster lies on the border of Laniakea, pulling matter from Laniakea toward itself. Tully's map showed that the boundary between superclusters is not a sharp edge, but a kind of gravitational watershed, a ridge where the flows diverge, some matter falling toward Laniakea's centre, and other matter falling toward neighbouring basins. We live in a cosmos of currents. Let me slow down here and let this settle. You are lying in the dark, perhaps with your eyes closed, perhaps already halfway to sleep, and you are falling. Not just toward the Great Attractor, but toward the Shapley supercluster, and toward every other lump of matter in the universe that happens to have more pull from your direction than the opposite direction. You are embedded in a gravitational flow that extends for billions of light years. You are part of a current that has been running since the Big Bang and will keep running until the universe ends. The room feels still, your body feels stationary, but stillness is an illusion of scale. Zoom out far enough and everything is in motion. Zoom out far enough, and the Earth is a mote of dust circling a mote of fire, and the mote of fire is falling through an ocean of ink, and the ocean of ink is draining toward a mass concentration you will never reach, and the mass concentration is draining toward another, and another, in a hierarchy of falls that has no bottom. This is not frightening. Or rather, it does not have to be frightening, it is simply true. It is the universe as it is, seen from the appropriate vantage point. The Great Attractor is not a monster or a doom. It is a fact of cosmic geography. We are falling toward it the way a river falls toward the sea. The river does not panic, it simply flows. And so do we. The question that haunted astronomers after the discovery of the bulk flow was whether this motion told us something deep about the universe, about its initial conditions, about the nature of dark matter, about the reliability of our cosmological models. If the universe began in a smooth, nearly uniform state, how did structures like the Great Attractor form? And if structures like the Great Attractor exist, are they consistent with our models of how gravity assembles matter over cosmic time? These are not idle questions. The entire framework of modern cosmology, the Big Bang, inflation, dark matter, dark energy, the cosmic microwave background, make specific predictions about how matter should cluster. The predictions can be tested against observations. If the observations match, the models are confirmed. If they do not match, the models must be revised or replaced. The Great Attractor was, in a sense, a test case. Could the standard model of cosmology explain a mass concentration this large, this nearby, exerting this much gravitational influence? The answer, it turned out, was yes, but only barely. The Great Attractor lies at the edge of what the models predict as typical. It is an unusual structure, a statistical outlier, the kind of thing that might form once in a volume the size of the observable universe, but would not be expected to form commonly. Its existence does not break the models, but it stretches them, and there are hints, still tentative, still debated, that the bulk flow may be even larger than the Great Attractor and Shapley together can explain. Some studies have suggested that galaxies are streaming coherently across distances of 1 billion light-years or more, all moving in roughly the same direction, as if pulled by something even larger and more distant than anything we have yet mapped. If these measurements are correct, they would pose a genuine challenge to standard cosmology. The universe should not be able to produce flows that coherent over scales that large. The debate continues. The measurements are difficult and different teams using different methods get different answers. But the possibility lingers, like a shadow at the edge of the data. Perhaps there is something out there, beyond the Shapley supercluster, beyond the Laniakea basin, that we have not yet seen. Perhaps the cascade of falls does not stop where our surveys end. Perhaps it continues, current within current, all the way to the edge of the observable universe and beyond. Let that possibility settle for a moment, a structure so vast, so distant, that our deepest surveys have not yet glimpsed it. A gravitational influence propagating across 1 billion light-years of emptiness, tugging at galaxies that have never exchanged a single photon of light. This is the kind of idea that would have seemed absurd a century ago. Today it is merely uncertain. Tomorrow it may be confirmed or refuted by observations that are already being planned. But before we look forward, we need to look down into the details of how astronomers actually measure these cosmic flows, down into the methodology that transformed vague suspicions into quantified certainties. Because the story of the Great Attractor is not just a story of what was found, it is a story of how finding became possible at all. Imagine you're standing at the shore of an ocean at night. The water is black, the horizon is invisible. Somewhere out there, beyond your sight, currents are moving. Water is flowing in patterns you cannot see. The only evidence you have is what washes up at your feet. Driftwood, seaweed, the occasional bottle. From these fragments, you're asked to reconstruct the entire circulation system of the ocean. This is roughly the position astronomers occupy. They cannot go to the Great Attractor. They cannot place instruments in the flow. They can only observe galaxies from a single vantage point, Earth, and try to infer the invisible currents from the motion of the galaxies they can see. The driftwood, in this case, is starlight, and the challenge is immense. The first tool astronomers use is something called a redshift survey. When light travels from a distant galaxy to Earth, the expansion of the universe stretches the light's wavelength. The faster a galaxy is moving away from us, or rather, the more the space between us has expanded, the more the light is stretched. Blue light becomes green, green becomes yellow, yellow becomes red, red becomes infrared. This stretching is called redshift, and it can be measured with extraordinary precision. You point a spectrograph at a galaxy, you identify the characteristic patterns of hydrogen or oxygen or other elements in its light, and you measure how far those patterns have shifted from their laboratory positions. The result is a number, a velocity expressed in kilometers per second, telling you how fast the galaxy appears to be receding. But here is the difficulty. The redshift you measure is the sum of two different motions. One is the Hubble flow, the recession caused by the expansion of space itself. The other is the peculiar velocity, the galaxy's own motion through space, caused by gravitational attraction to nearby mass concentrations. The redshift does not distinguish between these two contributions. It gives you a single number, and you must somehow separate it into its components. The Hubble flow is predictable. If you know a galaxy's distance, you can calculate how fast it should be receding due to expansion alone. The formula is simple. Velocity equals distance times the Hubble constant. A galaxy at 100 megaparsecs should be receding at roughly 7,000 kilometers per second. A galaxy at 200 megaparsecs should be receding at roughly 14,000 kilometers per second. This is the baseline, the expected value, the null hypothesis. The peculiar velocity is the deviation from this baseline. If a galaxy at 100 megaparsecs is receding at only 6,500 kilometers per second instead of 7,000, then it has a peculiar velocity of 500 kilometers per second toward us. It is moving against the Hubble flow falling in our direction. If it is receding at 7,500 kilometers per second, it has a peculiar velocity of 500 kilometers per second away from us. It is moving with the Hubble flow but faster, falling away. The problem is obvious. To calculate the peculiar velocity, you need to know the distance. But measuring distances in cosmology is notoriously difficult. Galaxies do not come with odometers attached. You cannot stretch a tape measure across 100 megaparsecs. You must rely on indirect methods, standard candles, standard rulers, empirical correlations, and every one of these methods carries uncertainty. This is where the Tully-Fisher relation enters the story. In 1977, Brent Tully and Richard Fisher discovered a tight correlation between two properties of spiral galaxies, their rotation speed and their intrinsic luminosity. Galaxies that spin faster are also brighter. The relationship is not perfect, but it is precise enough to be useful. If you measure how fast a galaxy rotates, which you can do by observing the Doppler shift of hydrogen gas in its disk, you can predict how bright it should be. Then you compare that predicted brightness to the brightness you actually observe, and the difference tells you the distance. A galaxy that appears 100 times fainter than its rotation speed suggests should be roughly 10 times farther away than you might have guessed. The Tully-Fisher relation gave astronomers a distance ladder that could reach beyond the local neighbourhood, out to several 100 million light-years. It was not the only method. There were also Cepheid variables, type Ia supernovae, surface brightness fluctuations, fundamental plane relations for elliptical galaxies, but it was one of the most widely applicable, and it was the Tully-Fisher relation, applied to the 7 Samurai sample of elliptical galaxies, that revealed the bulk flow toward the Great Attractor. Stop and feel the weight of that methodology. You observe a galaxy. You measure its spectrum, extracting a rotation curve from the Doppler shifts of its gas. You convert the rotation speed into a predicted luminosity using an empirical relation calibrated on nearby galaxies. You compare the predicted luminosity to the observed flux, deriving a distance. You use the distance to calculate the expected Hubble velocity. You subtract that from the measured redshift, obtaining a peculiar velocity. You repeat this for hundreds of galaxies, mapping the velocity field across a large volume of space. You look for patterns in the velocity field, coherent flows, convergences, divergences. You fit a model to the patterns, inferring the location and mass of the gravitational sources responsible. And from all of this, you announce that something invisible is pulling half the local universe toward itself. Every step introduces uncertainty. The Tully-Fisher relation has scatter. Galaxies of the same rotation speed do not all have exactly the same luminosity. Distance errors translate into velocity errors. Peculiar velocities are typically measured with uncertainties of 10 to 20%. For a single galaxy, this uncertainty is larger than the peculiar velocity itself. Only by averaging over many galaxies, looking for statistical patterns in the noise, can astronomers detect the signal of bulk flow. This is why the early measurements were so controversial. Different groups, using different samples and different calibrations, got different answers. Some found large peculiar velocities pointing towards Centaurus. Others found smaller velocities pointing elsewhere. Some claimed the bulk flow was resolved by the Great Attractor. Others insisted it continued beyond. The disagreements were fierce, and for years, the Great Attractor remained a contested concept rather than a settled fact. The resolution came slowly through better data. The 2-mass redshift survey, completed in the early 2000s, mapped the positions and redshifts of over 43,000 galaxies, creating the most complete all-sky view of the local universe ever assembled. The 60F Galaxy Survey added peculiar velocity measurements for thousands of galaxies in the southern hemisphere. Space-based observatories like the Wilkinson Microwave Anisotropy Probe and later the Planck satellite mapped the cosmic microwave background with unprecedented precision, revealing subtle imprints of large-scale structure on the oldest light in the universe. And the Cosmic Flows project, led by Brent Tully himself, 4 decades after his distance relation opened the field, began assembling comprehensive catalogues of galaxy distances and peculiar velocities, eventually encompassing tens of thousands of objects. The picture that emerged from this data deluge was both confirming and complicating. The Great Attractor was real. The bulk flow towards Centaurus was real. The Shapley supercluster was real, and it was contributing significantly to the pull. But the details were messier than the early models had suggested. The Great Attractor was not a single concentrated mass, but a broad overdensity spread across tens of millions of light-years. The Shapley supercluster was not a monolithic structure, but a collection of clusters arranged in a complex 3-dimensional web. And the velocity field was not a simple convergence toward a single point, but a complicated pattern of flows and counterflows, influenced by voids as well as overdensities. This last point deserves emphasis. We have been talking about the Great Attractor as if it were pulling us toward itself. But in the mathematics of gravity, pushing and pulling are 2 sides of the same coin. An overdense region pulls matter toward itself. An underdense region, a void, effectively pushes matter away, and the velocity field at any point is the superposition of all the pulls and pushes from everywhere. Consider what this means. When astronomers calculate that we are moving towards Centaurus at 600 kilometers per second, that motion is not caused by a single source. It is caused by the sum of every mass concentration and every void in the observable universe, each contributing its share according to the inverse square law. The Great Attractor contributes a large fraction. The Shapley supercluster contributes another. But there are also nearby voids, the local void, an immense region of emptiness adjacent to our local group, that push us away, effectively adding to our motion towards Centaurus. The final velocity is the vector sum of millions of individual contributions, some pulling, some pushing, some aligned with our motion, some opposed to it. This is the true nature of cosmic flow, not a simple fall toward a single attractor, but adrift through a landscape of hills and valleys, where every hill pushes and every valley pulls, and your trajectory is determined by the entire topography at once. Now let us zoom in on the Great Attractor itself. What is actually there? What have astronomers seen when they pointed their telescopes at the Centaurus direction and tried to peer through the zone of avoidance? The answer, achieved through decades of painstaking observation, is a region rich with structure. There is a galaxy cluster called Abell 3627, also known as the Norma cluster, which sits very close to the centre of the Great Attractor region. It contains hundreds of galaxies, ellipticals, spirals, irregulars, all orbiting within a common gravitational well. The Norma cluster is large, one of the most massive clusters within 250 million light-years, and it contributes significantly to the local gravitational pull. But the Norma cluster is not the Great Attractor. It is merely the densest node in a larger web. Surrounding it are other clusters: Centaurus, Pavo Indus, the clusters of the so-called Centaurus wall, all connected by filaments of galaxies, all embedded in a common overdensity that spans perhaps 200 million light-years. This entire structure, taken together, is what astronomers mean by the Great Attractor. It is not a single object, it is a region. It is a concentration of mass above the cosmic average, sufficient to produce a detectable gravitational influence on the surrounding universe. The infrared surveys were crucial to this mapping. Infrared light, with wavelengths longer than visible light, passes more easily through the dust of the Milky Way's disk. By observing at 2 microns instead of 0.5 microns, astronomers could see galaxies that were invisible at optical wavelengths. The 2-mass survey, the 2-micron all-sky survey, imaged the entire sky in near-infrared, revealing thousands of galaxies behind the zone of avoidance for the first time. Later surveys pushed deeper, detecting fainter and more distant objects. Radio observations, particularly of the 21-centimetre emission line of neutral hydrogen, provided another window, allowing astronomers to map the gas content and velocities of galaxies too dusty to see in any optical or infrared band. What emerged from these observations was a 3-dimensional map of the Great Attractor region. Not complete, not perfectly resolved, but far more detailed than anything available to the Seven Samurai in 1986. The Norma cluster sits at the heart. The Centaurus cluster, closer to us, sits in the foreground. A wall of galaxies extends from Centaurus toward Pavo Indus. Beyond Norma, the structure continues, merging eventually into the Shapley supercluster at twice the distance. And surrounding all of this, defining the boundaries of the overdensity, are voids, relatively empty regions that accentuate the contrast and amplify the gravitational influence. Let me give you a number to hold on to. The total mass of the Great Attractor region, including all its dark matter, is estimated at roughly 10 to the 16 solar masses. That is 10 quadrillion suns. If you could gather all that mass into a single sphere, it would have a diameter roughly comparable to the distance between our Sun and the nearest star, yet it would contain the mass of 10,000 Milky Way galaxies. But of course, the mass is not gathered into a single sphere. It is spread across 200 million light-years, diluted into clusters and filaments and individual galaxies. The concentration is subtle. The overdensity is perhaps a factor of 2 or 3 above the cosmic average, enough to dominate the local velocity field, but not enough to collapse into a single bound structure. This is the nature of the Great Attractor, a modest overdensity spread across an immense volume, exerting a persistent gravitational tug that accumulates over billions of years into immeasurable velocity. It is not dramatic in the way a black hole is dramatic. It is not concentrated in the way a galaxy cluster is concentrated. It is simply there, a broad depression in the gravitational landscape, and we are rolling slowly toward its centre. The journey will take a long time. At 600 kilometers per second, we cover roughly 20 million light-years every billion years. The Great Attractor is 250 million light-years away. At this rate, we might expect to arrive in roughly 12 billion years. But this calculation is misleading, because the Great Attractor is also moving. It is falling toward the Shapley supercluster. And the Shapley supercluster may be falling towards something else, and the Hubble flow, the expansion of space, is working against all of these motions, stretching the distances even as gravity tries to close them. The truth is that we will never reach the Great Attractor. The expansion of the universe, accelerated by dark energy, will eventually win. Structures that are not already gravitationally bound to us will recede forever. The Great Attractor, despite its pull, is not bound to the local group. Over cosmic time, it will drift farther and farther away, until it recedes past the cosmological horizon and becomes causally disconnected from us entirely. We are falling toward it now, but the fall is futile. The destination is unreachable. The river flows toward a sea it will never reach. There is something poignant in that image. All this effort, billions of years of gravitational work, quadrillions of solar masses exerting their subtle influence, and in the end the expansion wins. The structures unravel, the clusters drift apart. The galaxies that were once falling together begin falling away. The Great Attractor, which shaped the motion of everything within hundreds of millions of light years, becomes a memory, a relic of an earlier era when gravity could still compete with expansion. But we're getting ahead of ourselves. Before we contemplate the ultimate fate of the cosmic flow, we should examine the tools that allow us to understand it at all. The techniques that map peculiar velocities have advanced dramatically since the Seven Samurai, and the latest generation of surveys is revealing structures that would have been invisible just a decade ago. Consider the method called cosmic flows. Led by Brent Tully and his collaborators, this project assembles distance measurements from every available technique: Tully-Fisher, fundamental plane, type Ia supernovae, surface brightness fluctuations, Cepheids, and combines them into a single coherent catalogue. The latest iteration, Cosmic Flows 4, contains distances for over 55,000 galaxies, reaching out to nearly 1 billion light-years. From these distances, peculiar velocities are calculated. From the peculiar velocities, velocity fields are reconstructed, and from the velocity fields, the underlying mass distribution is inferred. The mathematics is elegant. Gravity is linear in the density field, double the overdensity, double the gravitational acceleration, and the velocity field is the integral of the acceleration field over time. This means that in principle you can run the equations backward. Start with observed velocities, infer the accelerations, reconstruct the density field. The mass map that emerges shows not only the visible galaxies but the invisible dark matter, halos that dominate the gravitational budget. The maps generated by cosmic flows are some of the most beautiful and haunting images in modern astronomy. They show a universe of filaments and voids, of basins and watersheds, of currents flowing toward invisible sinks. The Great Attractor appears as a broad depression in the gravitational potential, a valley into which everything nearby is draining. The Shapley supercluster appears as an even deeper valley beyond, and connecting them, like rivers connecting lakes, are channels of flow, regions where galaxies are streaming coherently, following the contours of the gravitational landscape. These maps also revealed something that earlier surveys had only hinted at. The basin of attraction we inhabit, the region whose galaxies are all flowing toward the same ultimate sink, is far larger than anyone had imagined. It extends not just to the Great Attractor, not just to Shapley, but to structures hundreds of millions of light-years in every direction. Tully and his collaborators gave this basin a name. They called it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is not a structure in the traditional sense. It is not bound by gravity. Its galaxies are not orbiting a common centre. It is more like a watershed, a region defined by the direction of flow rather than by physical cohesion. Just as rainwater falling on one side of a continental divide flows toward the Atlantic while water on the other side flows toward the Pacific, so galaxies in Laniakea are all flowing toward a common attractor basin, while galaxies in neighbouring regions flow elsewhere. The boundaries of Laniakea are not walls but saddle points, regions where the gravitational pull is balanced between neighbouring basins. Cross one of these boundaries, and you enter a different watershed, a different Laniakea, draining toward a different attractor. The Perseus-Pisces supercluster, for example, lies in a neighbouring basin. Its galaxies are not flowing toward the Great Attractor. They are flowing in a different direction, toward a different concentration of mass. The Laniakea map, published in 2014, changed how astronomers think about the Milky Way's place in the universe. We are not simply members of the local group, or the Virgo supercluster, or any of the other structures that had been defined before. We are citizens of Laniakea, inhabitants of a gravitational basin 500 million light-years across. Participants in a flow that will never reach its destination, but will continue for billions of years nonetheless. And yet even Laniakea may not be the end of the story. The bulk flow measurements that troubled earlier astronomers, the hints of coherent motion across 1 billion light-years, suggest that Laniakea itself may be drifting. The entire basin, with all its clusters and filaments and voids, may be falling towards something even larger. The name proposed for this hypothetical structure is the Shapley Basin, or sometimes the Great Attractor complex, a region that encompasses not just our local attractor, but the entire hierarchy of attractors out to the observable limit. The evidence is still uncertain. Measuring peculiar velocities at 1 billion light-years is extraordinarily difficult. The errors are large, the systematics are poorly understood, and different groups continue to publish conflicting results. But the possibility remains open. Perhaps the cascade of falls does not stop at Shapley. Perhaps there are structures beyond, unseen and unknown, pulling at everything we have mapped. Perhaps the universe is even more hierarchical than we imagined, with basins nested within basins, currents within currents, all the way out to the edge of observability and beyond. This is where the story of the Great Attractor merges with the story of cosmology itself. The structures we observe, the attractors, the basins, the flows, are relics of the early universe. They formed from tiny density fluctuations imprinted during inflation, amplified over billions of years by gravity. The size and distribution of these structures depend on the properties of dark matter, dark energy, and the initial conditions of the cosmos. By mapping the structures, we test the cosmological model. By finding anomalies, flows too large, attractors too massive, patterns too coherent, we probe the limits of our understanding. The Great Attractor, in this sense, is not just a gravitational curiosity. It is a probe of fundamental physics. Its existence confirms that gravity works as expected over scales of hundreds of millions of light-years. Its size tests whether the standard model of structure formation makes correct predictions. Its motion hints at structures beyond the surveyed volume, challenging us to look deeper. And so the observers continue their work. New surveys are planned, new telescopes are being built. The Vera C. Rubin Observatory, scheduled to begin operations soon, will image the entire southern sky repeatedly over a decade, discovering millions of transient events and billions of galaxies. The Nancy Grace Roman Space Telescope will survey the infrared sky with unprecedented depth, peering through dust and across cosmic time. The square-kilometre array, when completed, will map the hydrogen content of the universe out to redshifts, where the Great Attractor was still forming. Each of these instruments will contribute new pieces to the puzzle. Each will refine the velocity field, sharpen the mass map, extend the survey volume, and somewhere in that data, perhaps already recorded, perhaps yet to be collected, lies the answer to the question that has haunted this field since the Seven Samurai first noticed galaxies streaming towards Centaurus. What is out there? What is pulling us? And does the cascade of falls ever reach a bottom? The bottom, if there is one, would be a strange kind of destination. Not a place you could visit, not a point you could mark on a chart, but a centre of balance. A gravitational equilibrium where all the pulls cancel, and the universe stops falling toward anything. Whether such a place exists, even in principle, depends on questions that reach far beyond the Great Attractor itself. It depends on the shape of the cosmos, the total amount of matter, the behaviour of dark energy over billions of years, and the answers, as we'll see, remain genuinely uncertain. But before we can understand why the bottom might not exist, we need to understand what the fall actually looks like. Not in abstract terms, not as vectors on a map or numbers in a table, but as a physical experience. What would it mean to travel toward the Great Attractor? What would you see along the way? How would the journey change you? Let us conduct a thought experiment. Imagine you have access to a spacecraft capable of travelling at significant fractions of the speed of light. Not faster, because nothing with mass can cross that barrier, but fast enough that a journey of a few 100 million light-years becomes conceivable over a human-scale mission time. You launch from Earth. From this small rocky planet orbiting an unremarkable yellow star in the outskirts of an unremarkable spiral galaxy, your heading is fixed, toward the constellation Centaurus, toward the zone of avoidance, toward the region behind the Milky Way's disk where the Great Attractor lurks in gravitational silence. The first thing you notice as you accelerate outward is how empty the journey begins. The solar system falls away quickly. The ice giants, the Kuiper belt, the scattered disk objects that mark the frozen boundary of our sun's influence. Within hours or days, depending on your acceleration profile, you have left the Sun behind entirely. It becomes just another star, indistinguishable from its neighbours, then invisible among the millions of points that crowd the galactic plane. You're now travelling through the Milky Way's disk, a thin layer of stars and gas and dust that extends for tens of thousands of light years in all directions. The density here is higher than almost anywhere you will encounter on your journey. Roughly 1 star per cubic parsec, which sounds crowded until you realise that a cubic parsec is a volume of space you could fit 7 million suns inside with room to spare. The stars pass at intervals measured in light years. You do not encounter them exactly. At the speeds you're travelling, they appear briefly as points of light that shift in colour due to relativistic effects, then fall behind. The journey through the disk takes years, perhaps decades. The dust is thicker here, and your instruments show the infrared glow of star-forming regions, the radio emission of molecular clouds, the X-ray signatures of compact objects, neutron stars and black holes left behind by massive stars that burned too fast and collapsed. But you do not stop. Your destination lies beyond the Milky Way entirely, and the disk is merely the first of many obstacles. Eventually you emerge, the density drops, the stars thin. You're now in the halo of the Milky Way, a spherical region populated by ancient globular clusters, dim red dwarfs, and the invisible mass of dark matter that provides most of the galaxy's gravitational binding. The halo extends for hundreds of thousands of light years in all directions, far larger than the luminous disk that most people picture when they imagine a galaxy. And yet even here, the emptiness is palpable. The globular clusters are separated by tens of thousands of light years. The individual stars between them are scattered like dust motes in a cathedral. You cross the halo, you enter intergalactic space, and now the emptiness becomes something more profound. The Milky Way shrinks behind you. First a spiral pattern filling half your sky, then a glowing smear, then a point of light distinguishable from other points, only because you know which one it is. The local group surrounds you, but its members are scattered across millions of light years. Andromeda lies in a different direction, already falling toward the Milky Way on a collision course that will unfold over the next 4 billion years, but you are not heading toward Andromeda. You're heading toward Centaurus. You're heading toward the place where the gravity pulls hardest. The first structure you encounter, after months or years of empty void, is a filament. Not a single galaxy, but a chain of them. Dozens, perhaps hundreds of galaxies strung along a thread of dark matter that stretches for tens of millions of light years. The filament glows faintly in X-rays, heated by the gas that collects along its length. The galaxies within it are moving, not randomly but with a coherent drift, falling, like you, toward the attractor. You have joined a current. You're no longer travelling alone. The filament leads inward. The density increases. The galaxies come closer together, not close enough to collide, not yet, but close enough that interactions become visible. You see tidal tails stretching between neighbours, gas stripped from halos, bursts of star formation triggered by the stress. The universe here is more active than the void you left behind. Matter is accumulating. Gravity is doing its patient work. Ahead, the filament terminates in something larger, a cluster. Not Centaurus yet, but one of the smaller clusters that populate the near side of the Great Attractor region. Perhaps Hydra, perhaps Antlia, one of the many aggregations that the zone of avoidance partially hides. You approach the cluster's edge, and for the first time you encounter true density. The cluster contains hundreds of galaxies. They orbit a common centre, bound by gravity, moving at speeds of 1,000 kilometers per second or more. The space between them is not empty. It is filled with gas millions of degrees hot, radiating in X-rays with an energy output that dwarfs any individual galaxy. This is the intracluster medium, the diffuse plasma that constitutes most of the ordinary matter in clusters. It has been stripped from galaxies over billions of years, shocked to extreme temperatures by the violence of gravitational compression. You cannot see it with your eyes, but your instruments show you its presence. A glowing haze that extends for millions of light years in all directions. You pass through the cluster. The galaxies wheel around you in their slow orbital dance. Some are ellipticals, giant, featureless, red, their star formation long since exhausted. Some are spirals, their arms still winding, their disks still forming stars but disturbed now, warped by the gravitational tides. Some are irregulars, formless blobs of stars that have been torn apart by too many close encounters. The cluster is a graveyard and a nursery simultaneously. Old galaxies die here, their gas stripped, their stars scattered. New structures form from the debris, and still you continue. The cluster falls away, the filaments resume, the density fluctuates. Higher here, lower there. The universe arranged in the cosmic web that observations have mapped and simulations have predicted. You're travelling through the skeleton of creation, the pattern of matter left behind by the acoustic oscillations in the early universe, the ripples of density that began as quantum fluctuations and grew over 13.8 billion years into everything you see. The Great Attractor is not a point. You will not arrive at a location and stop. It is a basin, a trough in the gravitational landscape, and you are descending into it by degrees. The Norma cluster, when you finally approach it, is merely the densest concentration within the basin, the place where the most matter has collected, the bottom of the local depression. But even Norma is not truly the centre. The mass is distributed, the attractor is distributed. There is no singular destination, only a convergence. You slow as you approach Norma. The cluster is massive, one of the most massive in the local universe, though not the most massive known. Its gravitational influence extends for tens of millions of light years. The galaxies within it are ancient, their colours redder than those in younger clusters, their populations dominated by old stars that formed billions of years ago. The central galaxy, a giant elliptical, sits at the gravitational focus, a monster of trillions of stars that has grown fat by swallowing its neighbours over cosmic time. The X-ray emission is intense here, the intracluster gas hotter than almost anywhere else in the local universe. And yet, as you survey the scene, you realise something strange. The cluster is not at rest. Norma, for all its mass, is itself falling. The velocity field does not terminate here. The flow continues outward, toward Shapley, toward the concentration of clusters that lies beyond. The Great Attractor, it seems, is not the bottom of the gravitational hierarchy. It is merely a step, a way station, a local minimum in a landscape that continues to descend. This is what the observations show. This is what the velocity maps reveal. The cascade of falls does not stop at the structures we have named. Norma falls towards Shapley. Shapley may fall towards something larger still. And the question that no current observation can definitively answer, is whether this hierarchy ever reaches a terminus. To understand why the answer might be no, we need to think about what gravity does on cosmic scales, and how dark energy complicates the picture. Gravity, as Einstein described it, is the curvature of space-time caused by the presence of mass and energy. Matter bends the fabric of the cosmos, and other matter follows the curves. This is why galaxies attract each other, why clusters form, why the Great Attractor pulls at everything within its reach. But gravity has a competitor. Dark energy, the mysterious component that makes up roughly 68% of the universe's total energy content, does not attract. It repels. Or more precisely, it causes the expansion of space itself to accelerate. For most of cosmic history, dark energy was insignificant. When the universe was young and dense, matter dominated the energy budget, and gravity was the undisputed ruler of dynamics. Structures formed, clusters accumulated. The Great Attractors emerged from the primordial fluctuations. But about 5 billion years ago, the balance shifted. The universe expanded enough that the average density of matter dropped below a critical threshold, and dark energy began to win. The expansion started to accelerate, and the implications for gravitational flows became profound. Consider what this means for the Great Attractor. In a universe without dark energy, the basin we inhabit would continue to deepen. More matter would fall in. The flow toward Norma would strengthen. Eventually, over hundreds of billions of years, all the matter in the observable universe might collect into a single, unimaginably massive structure, a final attractor, a terminus of all gravitational hierarchy. But dark energy prevents this. The accelerating expansion stretches space faster than gravity can contract it, at least on the larger scales. Structures that are already bound, galaxies, clusters, the dense cores of superclusters, will remain together. But structures that are too diffuse, flows that span too great a distance, will be torn apart. The matter that is falling toward the Great Attractor will not all arrive. Some of it will be carried away by the expansion before it can reach its destination. The boundary between bound and unbound is not sharp, but it exists. Cosmologists calculate that the local group, the Milky Way, Andromeda, and a few dozen smaller companions will remain gravitationally bound. We will eventually merge into a single giant elliptical galaxy, an event sometimes called Milkomeda, that will unfold over the next several billion years. The Virgo cluster, close to the local group, will likely capture some nearby galaxies, but not all of them. The Great Attractor basin, Laniakea, is probably not bound as a whole. Its edges are already being stretched by dark energy. The flow toward Norma will continue for billions of years, but it will gradually weaken. Galaxies at the margins will stop falling and start receding. And beyond Laniakea, beyond Shapley, the structures there are already receding from us, carried by the expansion of space. We see them in the velocity maps as regions of infill, as concentrations of mass that exert their pull. But that pull is fighting a losing battle. Dark energy will eventually win. The largest basins will never drain. The deepest attractors will never attract their full potential. The cosmic flow, which once seemed to promise a final convergence, will instead fragment into isolated islands, clusters and superclusters that remain bound internally but drift apart from each other forever. This is the strange geometry of our universe. The Great Attractor is real. The flow is real. The fall is real. But it has no bottom, not because there is nothing at the centre, but because the universe itself is conspiring to prevent us from reaching it. Stop and feel the weight of that for a moment. We are falling. Our galaxy is falling. Everything we have ever known, every atom in your body, every photon that has touched your retina, is part of a current that stretches across hundreds of millions of light years, and that fall will continue for billions of years, longer than life has existed on Earth, longer than the sun will shine, but it will never complete. The destination we are falling toward will recede before we arrive. The matter that pulls us will be carried away by the expansion of the space between us. The basin will dissolve, the flow will dissipate, and the galaxies that survive will find themselves alone, adrift in a cosmos that has grown too large for gravity to bridge. This is not a catastrophe. It is not even particularly sad in any human sense. The timescales involved are so vast that no conceivable civilization could experience the entire process. What matters, perhaps, is the perspective it offers, a view of the universe as a system in tension, a landscape where competing forces shape the structures we see and the flows we measure. Gravity pulls, dark energy pushes, the universe evolves, and we, embedded in that evolution, are witnesses to a drama that began before Earth existed and will continue long after our sun has burned to a cinder. The Great Attractor, seen in this light, is not merely a gravitational anomaly. It is a snapshot of the universe in transition, a structure formed during the era when gravity dominated, now persisting into the era when dark energy will eventually triumph. The flow we measure is a fossil current, a relic of the universe's contracting past preserved into its expanding future. The studies that map this flow are not just astronomy. They are archaeology, excavating the history of the cosmos from the motions of its constituent parts. And this brings us finally to the deepest question the Great Attractor raises, a question that moves beyond observation, beyond measurement, beyond the technical details of velocity fields and mass distributions. It is a question about the nature of existence itself, about what it means to be part of a universe that flows and changes, that accumulates and disperses, that pulls and pushes in equal measure. What does it mean to be falling? We do not feel it. There is no sensation of acceleration, no wind in our hair, no vertigo in our stomachs. The fall is too slow, too smooth, too distributed across the vast scales of intergalactic space. Every atom in our bodies is falling together at the same rate, in the same direction. Einstein's principle of equivalence tells us that freefall is indistinguishable from weightlessness. We are falling, and we feel nothing. And yet the fall is real. The velocity field is measured, the peculiar motion is documented. 600 kilometers per second toward a region we cannot see, driven by a mass we cannot fully account for. The fall has been happening for billions of years. It will continue for billions more. and everything we do, everything we are, everything that will ever be born on this planet or any other, is swept along in that current. There is something humbling in this, something that resists the human impulse to feel central, significant, in control. We are not choosing our trajectory through the cosmos. We are not steering toward a destination. We are passengers on a galaxy that is itself a passenger, on a flow that is itself a passenger on a larger flow still. The cascade of falls extends beyond our sight, beyond our measurement, beyond our comprehension, and at every level we are carried along, oblivious to the motion, unable to alter the course. But there is also something magnificent in it. The same forces that shaped the Great Attractor also shaped us. The density fluctuations that seeded Laniakea also seeded the clouds of gas that collapsed to form the Sun, the protoplanetary disk that coalesced into Earth, the chemical complexity that eventually gave rise to life. We are made of the same matter that flows toward Norma. We are part of the same cosmic web that spans the observable universe. The fall is not something that happens to us from outside. It is something we are, down to the level of atoms and quarks and quantum fields. The Great Attractor, in this sense, is not a distant mystery. It is an intimate truth. It is the pattern we belong to, the current we swim in, the gravitational basin we call home, and the questions it raises about what lies beyond, about why the flow exists, about whether it ever reaches a terminus, are not just scientific questions. They are existential questions, questions about our place in a cosmos that operates on scales and timescales that dwarf everything we know. The observers will continue their work. The surveys will extend deeper into the zone of avoidance, probing the structures we have never seen. The velocity maps will sharpen, the mass estimates will improve, the simulations will become more sophisticated, and perhaps someday we will understand the Great Attractor completely. Every cluster, every filament, every concentration of dark matter laid bare in our instruments. But even then, the fall will continue. Even then, we will be carried along. Even then, the universe will flow, and we will flow with it, toward a destination that recedes faster than we approach, through a cosmos that expands faster than gravity can contract. The Great Attractor is real, the basin is real, the motion is real, and we are part of it, whether we notice or not, whether we understand or not, whether we ever fully grasp the immensity of what we are falling into. The telescopes point towards Centaurus, the data streams in, and the fall goes on. The fall goes on, but it is not the only story being told in this corner of the cosmos. There is a deeper question lurking beneath the maps and measurements, a question that has troubled astronomers since the first peculiar velocities were catalogued, since the first flow fields were drawn, since the first calculation suggested that something enormous was pulling at the fabric of space. The question is this: what happens when you try to see past the Great Attractor? What lies on the other side of the basin? For decades, the assumption was simple. The Great Attractor was the bottom of the well, the centre of the flow, the ultimate destination toward which everything in our cosmic neighbourhood was falling. The mass concentration near the Norma cluster was imagined as a kind of gravitational endpoint, a fixed point around which the local universe orbited or into which it slowly drained. The mental model was tidy. We were falling toward Norma. Everything nearby was falling toward Norma, and Norma presumably was sitting still, anchored in place by its own immense gravity, the centre of a vast sphere of influence. But the universe is rarely tidy. The more carefully astronomers mapped the velocity field, the more clearly a different picture emerged. The Great Attractor was not the bottom of the well. It was just a ridge, a local peak in the gravitational landscape, a feature that dominated our immediate neighbourhood, but was itself part of something larger. The flow did not stop at Norma. It continued past it, through it, beyond it, toward a region even more distant, even more massive, even more difficult to see. The first hints came from the same dipole measurements that had revealed the Great Attractor in the first place. If you subtracted the motion toward Norma from the cosmic microwave background dipole, there was still a residual signal. The galaxy was not falling toward Norma alone. It was falling toward something beyond Norma, something that added its own gravitational pull to the total peculiar velocity, something that lay at a distance where the zone of avoidance was even more impenetrable, and the measurements were even more uncertain. The astronomers who noticed this discrepancy were cautious at first. Residual signals can mean many things: calibration errors, systematic biases, local density fluctuations that distort the flow field in unexpected ways. The cosmic velocity field is not a simple thing to measure. Every data point is contaminated by distance uncertainties, by peculiar motions within clusters, by the difficulty of distinguishing true redshift from Doppler shift. A residual dipole could be noise. It could be an artifact of the analysis method. It could be a real signal pointing toward an even larger structure. The breakthrough came not from ground-based telescopes or infrared surveys, but from a statistical technique that had been developing quietly in the field for years. The method is called bulk flow analysis, and its premise is elegant in its simplicity. Instead of trying to measure the velocity of every individual galaxy and then fitting a flow field to the resulting data, you measure the average velocity of entire shells of space. You ask, what is the mean peculiar velocity of all galaxies between 50 and 100 megaparsecs from us? What is the mean velocity between 100 and 150 megaparsecs? What is the mean velocity between 150 and 200? If the Great Attractor at 80 megaparsecs were the only significant mass concentration affecting our cosmic neighbourhood, you would expect the bulk flow to decrease rapidly as you moved beyond it. Once you passed the attractor, the gravitational pull would be behind you, not ahead of you. The flow should weaken, fragment, lose coherence. Galaxies at 200 megaparsecs should be moving randomly, responding to local density variations rather than to a single dominant pull. That is not what the data showed. In 2008, a team led by Alexander Kashlinsky at NASA's Goddard Space Flight Center published a paper that sent shockwaves through the cosmological community. The team had measured the peculiar velocities of galaxy clusters not by traditional redshift methods, but by looking at tiny distortions in the cosmic microwave background called the kinetic Sunyaev-Zeldovich effect. When a cluster of galaxies moves through the bath of microwave photons left over from the Big Bang, the motion creates a characteristic signature. Photons passing through the hot gas of the cluster get scattered slightly, and if the cluster is moving toward us or away from us, the scattering shifts the apparent temperature of the microwave background in that direction. By measuring these tiny temperature shifts across hundreds of galaxy clusters, Kashlinsky's team could construct a velocity map that extended far beyond what traditional methods could reach. And the map told a startling story. The bulk flow did not diminish at the Great Attractor. It continued. It extended out to 800 megaparsecs, nearly 3 billion light-years, encompassing a volume of space far larger than anything that could be explained by known structures. And the direction of the flow was not perfectly aligned with the Great Attractor. It was tilted, pointing toward a region of sky that lay beyond Norma, beyond the Shapley supercluster, beyond everything that had been carefully catalogued in the maps of large-scale structure. Kashlinsky called this phenomenon the dark flow. The name was deliberately evocative, echoing dark matter and dark energy, the two great mysteries that had come to dominate cosmology in the late 20th century. But the implications of the dark flow were, in some ways, even more unsettling than those of its shadowy cousins. Dark matter was invisible, but its effects were local, operating within galaxies and clusters. Dark energy was diffuse, stretching space uniformly everywhere. The dark flow suggested something different, a gravitational pull so distant and so massive that it could impose coherent motion on everything within a sphere 3 billion light-years across. Let that scale settle into your mind for a moment. 3 billion light-years. That is more than a fifth of the observable universe. That is a volume containing hundreds of millions of galaxies, thousands of galaxy clusters, structures that have never exchanged a single photon with our own Milky Way because the light has not had time to travel between them. And yet, according to Kashlinsky's analysis, all of this, every cluster, every supercluster, every filament and void and concentration of matter, was moving together coherently in the same direction, pulled by something beyond the edge of measurement. The cosmological community was skeptical. Extraordinary claims require extraordinary evidence, and the kinetic Sunyaev-Zeldovich effect is a subtle thing to measure. The temperature shifts are tiny, parts per million against a background that already has variations at that level. Systematic errors could creep in from calibration uncertainties, from assumptions about the distribution of foreground objects, from the statistical methods used to extract the signal from the noise. Several teams attempted to replicate the result using independent data and different analysis techniques. Some found hints of coherent motion at large scales, others found nothing, or found motion in a different direction, or found that the apparent signal vanished when different statistical cuts were applied. The debate raged through the 2010s, with paper after paper offering confirmation or refutation, adjustment or reanalysis. The phrase dark flow acquired a contested status in cosmology, neither fully accepted nor fully rejected, hovering in the uncertain space between discovery and artifact. And beneath the technical arguments about data processing and statistical significance, a deeper question loomed. What could possibly produce a bulk flow at such scales? The standard model of cosmology, with its precisely calibrated parameters and its well-understood physics, had no room for coherent motion over volumes that large. In the lambda CDM framework, the universe is homogeneous and isotropic on the larger scales. Density fluctuations exist, but they average out. There is no preferred direction in space, no special point toward which everything falls, no master attractor that dominates the motion of hundreds of millions of galaxies. If the dark flow was real, it pointed toward physics beyond the standard model. It suggested that something was pulling on our observable universe from outside, from a region we cannot see, and perhaps can never see, from beyond the cosmic horizon that marks the edge of what light can reach in the age of the universe. Some cosmologists propose that the dark flow was evidence for pre-inflationary structure, remnants of density variations that existed before the epoch of cosmic inflation, and were stretched to scales larger than the observable universe. Others suggested that it might be the gravitational signature of a neighbouring bubble universe in an eternal inflation scenario, a sister cosmos whose mass was tugging at ours across the boundary of the multiverse. Still others argued that it was simply a statistical fluke, a noise artifact that would vanish with better data, or a systematic error that would be corrected with improved analysis techniques. The controversy remains unresolved. More recent measurements, including data from the Planck satellite's exquisitely precise maps of the cosmic microwave background, have generally failed to confirm the dark flow at the level originally claimed by Kashlinski's team. The most careful analysis suggests that if a bulk flow exists at very large scales, it is weaker and more uncertain than the early reports indicated. But they do not rule it out entirely. The measurements are still evolving, the techniques are still being refined, the question is still open, and in the meantime a different kind of answer has emerged from the continuing study of a large-scale structure. The dark flow may or may not be real, but the Great Attractor is definitely not the end of the story. Behind it, beyond it, partially hidden by it, lies something else, something larger, something that has come to be called, with admirable understatement, the Shapley supercluster. We have mentioned Shapley before, the dense concentration of galaxy clusters discovered by Harlow Shapley in the 1930s, the region that stood out even in the earlier surveys as unusually rich in galaxies, the structure that some astronomers suspected was playing a role in the peculiar motion of the local group. But the full significance of Shapley only became clear in the 1990s and 2000s as the maps of large-scale structure extended deeper and the mass estimates became more reliable. The Shapley supercluster lies approximately 650 million light-years from Earth, in the direction of the constellation Centaurus. It is not one cluster, but many, a sprawling complex of at least 24 major galaxy clusters, embedded in a web of filaments and walls that extends over a region roughly 100 million light-years across. At its heart lie some of the most massive clusters known in the local universe, including Abell 3558, Abell 3556, and the astonishing Abell 367, a structure so energetic that it hosts one of the largest known radio halos, a cloud of relativistic electrons spanning millions of light-years, lit up by the magnetic fields that thread the intracluster medium. The total mass of the Shapley supercluster is estimated at 10 quadrillion solar masses or more. That is 10 to the 16th power. That is 10 million billion times the mass of our Sun. That is roughly 10 times the mass of the Great Attractor, and it lies at roughly 3 times the distance. When you calculate the gravitational influence, the inverse square law tells you that Shapley's pull on the local group is somewhat weaker than the Great Attractor's. But it is not negligible. It is a significant contributor to our peculiar velocity. It is part of the answer to why we are moving at 600 kilometers per second toward a point in the sky that we cannot easily see. The realization that Shapley matters, that the Great Attractor is not alone, that our fall is driven by a combination of mass concentrations at different distances, changed the mental model once again. The picture was no longer a single basin with a single centre. It was a landscape of overlapping gravitational wells, nested and interacting, each one pulling at the matter within its sphere of influence while being pulled in turn by structures beyond. The Great Attractor was real, but it was not unique. It was one feature in a topology of attraction that extended as far as the surveys could reach. And the surveys kept reaching farther. The 2DEF Galaxy Redshift Survey, conducted in the late 1990s and early 2000s, mapped the positions and velocities of over 200,000 galaxies. The Sloan Digital Sky Survey, ongoing since 2000, has now catalogued more than 1 billion objects, including detailed spectra for millions of galaxies that allow their distances and velocities to be measured with unprecedented precision. The 6DF Galaxy Survey extended the coverage into the southern sky, probing the zone of avoidance from Australian telescopes, filling in the blank regions that had frustrated Lyndon Bell and Rubin and the other pioneers of peculiar velocity research. Each survey refined the picture. The Great Attractor sharpened into focus as a ridge in the density field, a region of modest overdensity dominated by the Norma cluster and its companions. Shapley emerged as the true giant of the local universe, the most massive structure within 1 billion light-years, the dragon that had been hiding in plain sight behind the dust of the Milky Way. And the velocity field itself became a river with tributaries, a flow that gathered matter from all directions and channeled it toward a complex of destinations that no single mass concentration could explain. The question of what lies beyond Shapley remains open. The surveys thin out at those distances. The uncertainties grow. The zone of avoidance widens because the dust of the Milky Way does not care how hard astronomers try to see through it. There may be structures beyond Shapley that contribute to the flow. There may be voids that shape the field in ways we have not yet mapped. There may be, at sufficiently large scales, a true averaging out, a point at which the peculiar velocities diminish to zero and the cosmic expansion takes over completely. Or there may not be. The data is still incomplete, the picture is still fragmentary, the fall continues, and we do not yet know where it ends. But we do know something remarkable about the structures we have found. We know that they are not accidents. They are not random concentrations of matter that happen to form by chance in an otherwise uniform universe. They are the inevitable consequences of gravity working on density fluctuations over cosmic time. They are the signatures of a process that began in the first moments after the Big Bang and has continued, uninterrupted, for nearly 14 billion years. The Great Attractor and the Shapley supercluster and the filaments of the cosmic web are all part of the same story. The story of how gravity builds structure from nearly nothing, how small variations in density grow into the scaffolding of the universe. The seeds were planted in the epoch of inflation, that unimaginably brief period when space expanded faster than light and quantum fluctuations were stretched to astronomical scales. The variations were tiny, parts per 100,000, barely measurable even with the most sensitive instruments. But they were there, imprinted on the fabric of space, waiting for gravity to find them. And gravity did find them. The slightly overdense regions pulled in more matter. The accretion made them denser still. The feedback loop ran for billions of years, and the result was the cosmic web we see today. The filaments and walls and clusters and voids, the Great Attractor and Shapley and Laniakea, and all the structures we have named and all the structures we have not. The process is still happening. It will continue to happen for billions of years to come. Gravity does not stop. The fall does not end. The matter of the universe keeps flowing toward the densest regions, clustering ever tighter, building ever more massive structures on ever larger scales. But there is a limit. The expansion of space is accelerating, driven by dark energy, and eventually the expansion will outpace the growth. Structures that are not already gravitationally bound will drift apart, the flow will slow, the river will dry up, and the cosmic web will freeze into a static pattern, each cluster an island universe, each supercluster isolated by vast empty distances that grow faster than anything can cross them. That future is billions of years away. For now, the fall continues. For now, the matter streams toward the attractors. For now, we are part of the flow, carried along by forces we did not choose and cannot resist. falling toward a destination we can only partially see. The telescopes keep watching. The velocity maps keep improving. The surveys extend deeper into the zone of avoidance, probing the structures that hide behind the veil of our own galaxy. And somewhere out there, beyond the edge of what we can measure, the universe continues to expand. Indifferent to our questions, indifferent to our instruments, indifferent to everything except the fundamental laws that have governed its evolution since the beginning of time. Gravity pulls, space stretches, matter falls, and the Great Attractor, that unnamed ridge in the cosmic landscape, that gravitational basin we happen to find ourselves within, continues to shape the motion of hundreds of thousands of galaxies, including the small blue world where someone is lying in the dark, wondering what it all means. What it all means is a question that deserves an honest answer, even if the honest answer is that we do not entirely know. But we know more than we did, and perhaps the knowing itself is a kind of meaning, a thread we can hold on to as we drift through the dark. Let me try to put it all together now, slowly, carefully, the way you might assemble a map of a place you have only glimpsed through fog. We began with motion, the simple fact that our galaxy is moving, not just with the expansion of space, but against it, towards something. We measured that motion at 600 kilometers per second, and found ourselves puzzled. The Virgo cluster, the obvious candidate, was not enough. Something larger was pulling, something hidden behind the bright band of the Milky Way, behind the dust and stars and gas that obscure a full fifth of the extragalactic sky. We called it the Great Attractor because we did not know what else to call it. The name was provisional. It suggested a single massive object, a cosmic magnet drawing everything toward itself. But the reality turned out to be both simpler and more profound. There is no single object. There is no monster lurking in the zone of avoidance. There is only the landscape of space-time itself, shaped by the distribution of matter, curved into valleys and ridges that guide the flow of everything within them. The Great Attractor is a ridge, a local concentration of mass, yes, but not the ultimate destination. Beyond it lies the Shapley supercluster, 50% more massive, the true dominant weight in our corner of the universe. And beyond Shapley lie structures we are only beginning to map, basins and walls and filaments extending outward in every direction, the cosmic web spinning itself across hundreds of millions of light years. We are not being pulled so much as we are falling. The distinction matters because it changes the nature of the question. To ask what is pulling us implies an external force, an active agent, something reaching out and grabbing hold. But nothing is reaching out, nothing is grabbing. There is only the geometry of space curved by mass, and the natural tendency of all things to follow the curves. We fall because the universe is not flat. We fall because mass bends space. We fall because that is what matter does in a curved universe, has always done, will always do, until the acceleration of dark energy tears the structures apart. The fall has been happening for nearly 14 billion years. It started before there were galaxies to fall, before there were stars, before there were atoms. It started in the first moments after the Big Bang, when quantum fluctuations were stretched to cosmic scales and imprinted on the fabric of the universe as tiny variations in density. Parts per 100,000. Barely there, almost nothing. But enough for gravity to notice, and gravity noticed. Gravity always notices. The slightly overdense regions pulled in a little extra matter. The extra matter made them denser still. The denser regions pulled in even more matter. The feedback loop ran without pause for billions of years, and the result was everything we can see through our telescopes tonight. The stars, the galaxies, the clusters and superclusters, the filaments of the cosmic web, the Great Attractor, the Shapley concentration, Laniakea, our home supercluster, 100,000 galaxies bound together by gravity into a single enormous structure, streaming toward a common centre of mass. We are part of this, not observers watching from outside, participants, passengers on a galaxy that is itself a passenger on a larger flow, falling through curved space-time toward destinations we can only partially see. The fall is invisible to us because we cannot feel it. We have no fixed point to measure against, no anchor in absolute space, because absolute space does not exist. There is only relative motion, and from our perspective, everything seems still. The Milky Way seems motionless, the stars seem fixed, the night sky seems eternal, but the appearance is an illusion created by our speed, our size, our brief lives in a universe that operates on timescales we can barely imagine. We are moving at 600 kilometers per second. Every hour we're 2 million kilometers closer to the Great Attractor. Every year we're 17 billion kilometers further along the fall, and it makes no difference at all to our lives, to our plans, to our hopes and fears and daily concerns. The motion is real, but imperceptible. The fall is happening, but unfelt. We will never arrive, not in any meaningful sense, not in any time frame that matters to human beings. The journey will take billions of years, and even then, the destination itself is moving, receding, part of a larger flow that extends beyond anything we have yet mapped. This is the vertigo I promised at the beginning. Not fear exactly, not dread. Something more like awe, tinged with humility. The realization that we are embedded in processes so vast and so slow that they make our entire existence seem like the briefest flicker, a single frame in a film that runs for billions of years. But here is the strange thing. Here is the part that keeps me returning to this subject, night after night, tracing the velocity fields and the density maps and the cosmic flows that carry us all. We found it. We are the brief flickers, the transient patterns of matter that somehow became aware of themselves, and we found the Great Attractor. We noticed the anomalous velocity. We measured the dipole in the cosmic microwave background. We built infrared telescopes to peer through the zone of avoidance. We mapped the redshifts of tens of thousands of galaxies. We calculated the distances and the velocities and the peculiar motions. We traced the flow backward to its source, or forward to its destination, and we put names on structures that had existed for billions of years without names, without observers, without anyone to wonder what they were. The Great Attractor did not care about being discovered. The Shapley supercluster will not notice our attention. Laniakea will continue its slow collapse whether we watch or not. But we watch anyway. We name anyway. We wonder anyway. And in that wondering, in that stubborn insistence on understanding a universe that has no obligation to be understood, there is something that might, if you look at it from the right angle, resemble meaning. Stop and feel that for a moment. Hold it in your mind like a small warm thing cupped in cold hands. You're lying somewhere in the dark, on a planet that is falling toward a supercluster, inside a galaxy that is falling toward a greater concentration of mass, inside a cosmic web that is itself evolving, clustering, thinning, pulled apart by dark energy even as gravity tries to hold it together. You are made of atoms that were forged in stars that died before the Earth was born, atoms that have been falling through curved space-time for billions of years, and will continue falling for billions more. And somehow, through some process we do not fully understand, those atoms have arranged themselves into patterns that can ask questions, patterns that can build telescopes, patterns that can measure peculiar velocities and trace cosmic flows, and give names to things that did not know they needed names. That is either the strangest coincidence in the universe or the most remarkable thing about it. I cannot decide which. Perhaps it is both. The Great Attractor taught us something about ourselves, something we might not have learned any other way. It taught us that we are not at rest. It taught us that stillness is an illusion, that motion is the fundamental state of everything, that the universe is not a place where things sit, but a process through which things flow. It taught us that the cosmos has structure, not random structure, but orderly structure, patterns built by gravity over billions of years, patterns that continue to evolve and change even as we watch. And it taught us that we are part of those patterns, woven into the fabric of the cosmic web, falling along with everything else toward destinations we may never reach. There is a certain peace in that, if you let yourself feel it. The fall is not something happening to you. You're not being dragged against your will. You're simply part of the flow, part of the great slow migration of matter through space-time, and you always have been. Before you were born, the Milky Way was falling toward the Great Attractor. After you are gone, it will still be falling. Your existence is a brief participation in a process that stretches back to the beginning of time and forward to the end of everything. You did not choose it, but you do not have to resist it either. You can simply let yourself be carried, the way a leaf is carried by a river, the way the river is carried by the slope of the land, the way the land is carried by the motion of a planet that is itself carried by the motion of a galaxy, that is itself carried by the curvature of space-time toward a ridge in the density field, that someone once called the Great Attractor. Let me give you one more image before we close. Imagine standing on a beach at night, looking out at the ocean. The water is black and the horizon is invisible, and the only thing you can see is the faint phosphorescence of waves breaking on the sand. You know the ocean is vast. You know it extends beyond the limits of your vision, beyond the curve of the earth, to shores you will never see. But you cannot see the vastness. You can only see the small bright line where the water meets the land, the edge of something enormous that hides its scale in darkness. The visible universe is like that beach. The Great Attractor is out there, somewhere beyond the zone we can clearly see. The Shapley supercluster is beyond that, and beyond Shapley, who knows what else waits in the dark. More mass concentrations, more cosmic flows, more basins and ridges in the density field, shaping the motion of galaxies we will never observe. We stand on our small bright edge and peer into the black, and we name the things we can see, and we wonder about the things we cannot, and we know that the ocean is larger than any map we have drawn so far. The telescopes will keep improving. The surveys will keep extending. The zone of avoidance will slowly yield its secrets as infrared instruments become more sensitive, as radio observations fill in the gaps, as new techniques allow us to see what dust and stars have hidden. We will learn more about the Great Attractor. We will refine our estimates of its mass, its extent, its relationship to larger structures. We will trace the cosmic flows further and further into the unmapped regions, building an ever more detailed picture of the landscape through which we fall. But we will never see all of it. The universe is too large. Space is expanding. The most distant galaxies are already receding faster than light can travel, and they will never send us information about their peculiar velocities, their local flows, their participation in cosmic structures beyond our horizon. We are confined to our observable bubble, our finite sphere of accessible light, and everything beyond that horizon is lost to us forever, present but invisible, real but unreachable. The Great Attractor reminds us of that confinement. It sits at the edge of what we can see, half hidden behind the zone of avoidance, a concentration of mass that influences our motion but refuses to be fully mapped. It is a lesson in humility, a reminder that the universe does not arrange itself for our convenience, that some things are hard to see not because we lack the technology, but because of where we happen to be standing, because of the dust in our own galactic plane, because of the accidents of position that put certain things in shadow and others in light. And yet we saw it anyway. We noticed the anomaly, we measured the motion, we traced the cause, we did what humans have always done, which is to look at the darkness and refuse to accept that it is empty, to probe and question and name until the unknown becomes, if not fully known, at least a little less strange. The Great Attractor is not strange anymore, not truly strange. It is mapped, measured, understood within the framework of our cosmology. It is a local overdensity in a universe full of overdensities and underdensities, a ridge in the cosmic landscape, a basin toward which matter flows. It obeys the same laws that govern everything else. It has no special properties. It is not magical. It is not anomalous in any fundamental sense. It is simply a place where there is more mass than average, and mass bends space, and matter falls along the bends. What remains strange is that we found it. What remains strange is that matter can become aware of itself, can build instruments to measure its own motion through space-time, can trace the flows that carry it toward destinations it will never reach. What remains strange is consciousness, the fact that the universe is not just expanding and clustering and flowing, but also, in at least one small corner, asking what it is doing and why. We do not know why there is something rather than nothing. We do not know why the laws of physics are what they are. We do not know why consciousness exists, or how it arises from matter, or what it means that matter can know itself. These are questions that lie beyond the scope of our current understanding, perhaps beyond the scope of any understanding we will ever achieve. But we know that we are falling. We know that the Great Attractor is real. We know that the universe has structure, that gravity builds complexity from simplicity, that small fluctuations in density grow over billions of years into the cosmic web we see today. And we know that we are part of that web, embedded in its filaments, carried by its flows, participants in a process that is so much larger and older and slower than anything a human life can comprehend. The fall will continue. For billions of years, the Milky Way will drift toward the center of Laniakea. For tens of billions more, the local structures will merge and concentrate, pulled together by gravity even as dark energy pushes the larger universe apart. And eventually the acceleration will win. The expansion of space will outpace the gravitational collapse. The flows will slow, the structures will freeze, and the cosmic web will become a collection of isolated islands, each cluster alone in a void that grows faster than light can cross it. That future is very far away, so far that the sun will have burned out, the Earth will have been swallowed or scattered, the Milky Way will have merged with Andromeda, and perhaps a dozen other galaxies. By the time the flows stop, there will be no one here to notice, unless we have found ways to travel that we cannot yet imagine, unless we have become something other than what we are now, unless the brief flickers have learned to persist. But that is a different story for a different night. For now, there is only this, you in the dark, the Great Attractor hidden behind the veil of the Milky Way, the slow, invisible fall that connects you to structures hundreds of millions of light years away, to processes billions of years old, to a cosmos that did not make itself for you but somehow made you anyway. The night sky looks still, the stars look fixed, the universe looks eternal and unchanging, but you know better now. You know that everything is moving. You know that the stillness is an illusion. You know that you are falling, have always been falling, will continue falling for as long as you exist and long after you are gone. And perhaps knowing changes nothing. Perhaps the Great Attractor makes no difference to your life, to your plans, to your morning and your evening and the small concerns that fill your days. Perhaps the cosmic flow is irrelevant to everything that matters to you, and that is fine, that is appropriate, that is the way it should be. We live at human scales, and cosmic scales are not our home. But sometimes, late at night, when the world is quiet and the stars are out, and you find yourself wondering what it all means, it is worth remembering that you are not alone in your motion, that hundreds of thousands of galaxies are falling alongside you, that the universe is not indifferent to you in any personal sense, because the universe is not a person, but it is connected to you in ways that run deeper than you can feel, through the curvature of space-time itself, through the gravity that shapes all motion, through the cosmic web that holds everything in its invisible threads. You are part of something enormous. You have always been. The Great Attractor is simply a name for one of the structures that shape that enormity, one ridge in the landscape, one destination among many. The fall toward it is simply the way matter moves in a curved universe, the same way it has always moved, the same way it always will. The telescopes keep watching, the data keeps coming in, the maps keep improving, and somewhere, right now, the light from the zone of avoidance is crossing the last few million years of space toward instruments that will capture it, analyze it, add it to our understanding of the structures that hide behind the stars. We fall without feeling, we move without knowing, and yet somehow we notice. Somehow we measure. Somehow we ask. That may be the strangest thing of all, that the universe can know itself, even partially, even imperfectly. That matter can arrange itself into patterns that wonder about patterns, that someone, somewhere, lying in the dark, can hold in their mind an image of the Great Attractor and know that they are falling toward it and feel something like peace at the scale of it all. The night is long, the fall is longer, and somewhere beyond the edge of what we can see, the universe keeps expanding, keeps clustering, keeps building structure from nearly nothing, indifferent and beautiful and vast beyond all imagining. Rest now. Let the motion carry you. The Great Attractor will still be there in the morning, hidden behind the veil, shaping the paths of galaxies, waiting for no one, patient as gravity itself. You are falling. You have always been falling. And in the falling, strangely, there is something that feels almost like home.